Oh yes, thank you. First of all, many thanks to the organizer for this very beautiful conference and for giving me the opportunity to tell you some work in progress with Bernardo, Gareth, and Enrico in Utrecht, and something that I did with David, Enrico, and Filippo before. So, more or less, this is the outline and the introduction. I don't have to say anything, add anything about inflation. We know that we have some data. In fact, we have many models. The idea is, along what Leonardo Senatore has been talking about, is trying to understand something without relying on specific UV models. So, using a model-independent point of view as much as possible. I try to be very, very basic, so I want to leave you a couple of messages. The first one is very simple regarding shift symmetry. I'm not that ambitious as Leonardo Senatore has been. I'm not talking about supersymmetry, but just a shift symmetry for a single clock inflation. And then I've discussed the case in which higher derivative operators become important. So I don't want to say anything about the EFT of inflation because we heard this morning Giovanni and Lorenzo already, and Leonardo Senatore has done it better than I could do. So we've heard that we can write down the action, which is an arbitrary function of Riemann properly contracted, G00 the extrinsic curvature, and covariant derivatives and functions of time, because now you have only spatial diffeomorphisms left, while time diffs are broken. And now you expect, because one gauge symmetry is not there anymore, you have one extra degree of freedom. So this action generically describes three propagating degrees of freedom, and then you can expand around the FRW. But let me stress a point beyond what Leonardo has already said. That at this level, this is not the EFT of inflation, but this is the EFT of every single clock cosmology. So there is no input here for the moment, either from inflation or from additional symmetries. Okay, let's start with, let's be very basic. I want to discuss the simple case in which I don't have a higher derivative. So let's consider powers of the metric fluctuations with some arbitrary coefficients which are time dependent. Of course, M0 and 1 are fixed by the background, but yet there is infinite freedom here because these coefficients are arbitrary functions of time in principle. And this happens already in a P of X theory where X is this combination. And if the background is an arbitrary function of time, these are arbitrary. But the point is that let's impose a shift symmetry in this action. Imposing a shift symmetry for the clock means imposing a very specific time diff. So if you do this, if you play this game here in this action, you discover that these functions actually are related to each other. In practice, you have that the coefficient n plus 1 is related to Mn through this chain of differential equations. I'm saying something very, very basic. Maybe the best way to understand this point is do a time reparameterization. So instead of using t as your time, you can rewrite your effective theory using phi as your clock. So you can rewrite the action. Here I'm using phi, and the statement of a shift symmetry is nothing but saying that your action does not depend on phi explicitly. And so this is, if you want, this condition is telling us that all these functions are functions of Zlorov parameters. In other words, if you neglect contributions from higher derivatives, you have a prediction, for instance, for FNL. So C3 tilde is a very specific function of Zlorov parameters. In other words, you have a line or in this is the curve that I wrote here. So one might be interested, for instance, in trying to understand this a little bit better using word identities and so on, but the main message is that if you neglect higher derivatives, you can write these functions of time in terms of Zolorov parameters. And at this level, using the EFT is very nice to see how how to write down the equations of motion, because if you take the quality divergence of the energy momentum tensor, you discover that these are the equations of motion, which are only consequences of n0 and n1. So at this level, it's very nice to see that you cannot have Zolorov in P of x theories, because either epsilon is exactly 0, so you have an exact de Sitter, or you have eta to be of order 1 at least. So this is already known, but it's very easy to see at this level. So this is teaching us that if you want to have a standard Zolorov, so a regime in which epsilon and eta are both small, you need to have higher derivatives, which typically are suppressed. So you have to say something more about these operators. So let's try to do that, to play this game. So here I'm using n, but nothing is not different. So this line is the previous one, plus dot dot dot, and then I'm adding the extrinsic curvature. So the next simple step, you can add other operators, but you can look, for instance, here for a classification of the unitary gauge language. So typically, let's focus on these two for simplicity. You expect, of course, that physical observables are predominantly determined by the operators, of course, with the least number of derivatives in the spirit of an effective field theory. So what I'm saying is that if you are within the regime of validity of your effective theory, delta n, delta k is always suppressed with respect to delta n squared. This is in general true, but unless, in principle, you can have some symmetry that enhances the operator. And the message that I want to leave you is that, indeed, you can do that if you, and the symmetry that allows you to do that is a weakly broken Galilean symmetry. So in theories, if you assume that your effective theory has a weakly broken Galilean symmetry, you can have these two operators of the same order, without exiting the regime of validity of your effective theory. Let's see how it works. So without going into details, so forget about the formula. So I want just to introduce in a couple of words what a Galilean symmetry is. So in some sense, it's an extension of a sheaf symmetry for the scalar field. It's nothing but then it's a shift for the scalar field. You can show that in flat space-time there are 4 operators you can write down. But so, for instance, you have the kinetic term or d phi squared box phi. The point is that these operators have a very important property, which is the no-renormalization theorem. So the loop corrections to these operators are exactly 0. So the couplings of these operators are not renormalized at all. Of course, gravity breaks the symmetry explicitly, but I want to convince you that there is a subclass of theories in which the breaking of the symmetry is not too bad, in the following sense. So, of course, you have to choose a particular coupling to gravity, but you can prove that if you choose this coupling here, quantum corrections to the operators d phi to the 2n are suppressed by this scale. And one can prove that if you chose a different coupling to gravity, you would discover that quantum corrections are suppressed by a lower scale. So this is the best you can do. So in other words, this coupling produces quantum corrections which are suppressed by the highest scale, which whose smallest value can be lambda 2, this scale here. So we called this subclass of theories the theories with a weakly broken Galilean symmetry, because you have a sort of remnant of the non-renormalization theorem. So the point, the point of this result is the following: is that you can, even if in this subclass of theories you can have that the lower derivative operators, so d phi, so operators in which phi is differentiated only once, are of the same order as higher derivative operators, provided that they are suppressed by a different scale. So you see, I'm suppressing here higher derivative operators with the lambda 2, while higher derivative operators are suppressed by the cutoff. And you can do that without exiting the regime of validity of your effective theory. So this would be a problem if you didn't have a non-renormalization theorem that does the job. So in the unitary gauge language, this means that these two operators can be of the same order. And this enhancement is very is useful in the sense that this operator can be relevant, for instance, for non-Gaussianity. So you can have FNL greater than 1. So the point, let me set this point a little bit better, because typically if you have an effective theory, you can show that the FNL greater than 1 is not possible without exiting the regime of validity of your effective theory, unless you can either resum the series, and this is what happens in dBi inflation. dBi inflation, you know that you have the powers of delta n. You can have FNL 1 over CS squared, so FNL very big if CS is small, the speed of sound, because you can resum the series, because the coefficients are not arbitrary, so you know the resummation. The second point, and this is the message I leave you, is that you can allow for FNL greater or of order 1, also in the case in which you have a non-renormalization theorem, such that you can in some sense suppress higher derivative operators with a lower scale, or if you wish, you are enhancing the contribution to higher derivative operators without spoiling the consistency of your effective theory because of the non-renormalization theory. So this is the philosophy, and this is why you can, these two operators can be consistently of the same order once you expand around the inflationary background, and you can allow for FNL greater than 1. So just to give a very rough picture, so you can put constraints in the parameter space. These are the color of the region are ruled out, for instance, by R or FNL. You can see that if you reduce R, the region shrinks, but I chose epsilon to be a disorder. Of course, if you decrease this, if you choose a smaller value for epsilon, this region opens again. So, but just to summarize a little bit, what I want to do is just to give you a few concepts about trying to understand the role of the shear symmetry, whether it is exact or broken, what the degree of breaking is, and saying something about the role of higher derivative operators in the spirit of the effective theory of inflation. So I think I can stop here.